Hello everyone, my name is Nabangshu Sinha and today I will give a presentation on video super resolution using deep learning. This is the outline of my presentation. First, I will introduce the problem, then I will discuss some of the challenges which need to be solved in this problem. Then I will take a specialized case of this problem, which is single image super resolution, which is basically the super resolution of a single image. I will discuss the challenges in single image super resolution and then go for some deep learning solutions. When I say deep learning solutions, I mean the solutions which have used deep learning as part of their solutions. Next, I will move towards video super resolution. I will discuss some challenges in video super resolution. Although videos can be seen as extensions of single images, however, there are some additional challenges which need to be tackled for video super resolution. Next, I will go for some deep learning solutions for video super resolution. Then I will go for some future work, which more or less include the challenges which still need to be solved. And finally, I will conclude this presentation. So, before understanding video super resolution, we must first understand single image super resolution. This is super resolution of one image. Video super resolution can be seen as simply an extension over time of a single image super resolution problem. Basically, a video can be considered as a number of images which are connected through time. For example, a ball moving in space, or a bike moving on a road, etc., etc. Super resolution is basically the upscaling of low resolution images to high resolution images with minimum reduction in image quality. In other words, when we zoom into a picture, most of the time we lose, or I should say every time we lose information as we zoom closer and closer to see details which are very minute. And all digital images have a certain amount of minimum resolution beyond which they cannot provide uh, intelligible information. We cannot discern the different features in the images. So super resolution is a way to provide additional information at those levels. Here you can see an example of a distant part of a building which, when magnified, would have been completely a vague collection of pixels. However, because of a well-known a single image super resolution model, we can still get some discernible features in the highly magnified image on the right. Okay, so there are some challenges or some fundamental challenges in single image super resolution. First challenge is that this problem is ill-posed because we're going from let's say a matrix which uh, is, let's say, n by n, and we want to project this matrix into to a matrix of higher order, basically from n by n cross n to maybe 2n cross 2n, which basically requires us to provide additional information. And due to this, it can be said that multiple higher order matrices exist which can be downsampled to this one lower order matrix. So as such, uh, there are there are infinitely many solutions. So uh, we need to restrict or reduce the solution space for a particular low resolution image. The second challenge is that the upscaling factor decides the problem complexity, meaning an upscaling factor of 2 or 4 uh, are not the same problems. For example, or if I may go to extreme cases, upscaling factor of 2 and the upscaling factor of 100 are not the same problems. An upscaling factor of 100 is a highly complex problem. However, the upscaling factor of 2 is also a highly complex problem. However, the level of complexity for an upscaling factor of 2 is much lower, significantly lower than an upscaling factor of 100, which requires us to add or interpolate an enormous amount of information. The third challenge is that the quality assessment metrics, for example PSNR, the peak signal to noise ratio, or SSIM, the structural similarity, are not correlated to human perception, and as such we don't have any way for objectively evaluating the quality of an image. This makes it very difficult for us to properly judge the outputs generated by different models. So moving on to the solutions, there are multiple solutions for single image super resolution. There are many deterministic algorithms for single image super resolution. By deterministic, I mean that there is a fixed set of procedures which any computer or any system or any computational system must follow in order to produce a high resolution image from a given low resolution image. Some common deterministic methods are bilinear interpolation, bicubic interpolation. These are basically interpolation methods with different splines. For example, a bilinear interpolation method considers a linear spline, and a bicubic interpolation method considers a cubic spline. We can go for higher degree splines. However, it does not add any more information than which are already provided by these methods. In common literature, bicubic interpolation is the most common deterministic method used. Recently, deep learning techniques have been used for super resolution. This is hardly a surprise since most fields in computer vision have seen the advent of deep learning, and this is because of the amount of, or the tremendous amount of data that we have right now, and as such we are, and also of course significantly powerful computational units that we have right now, which allow us to train huge deep learning models. And these are data-driven models, and as such have very good results for such tasks. And so the results of deterministic algorithms, such as bicubic interpolation, are not good compared to data-driven models, such as CNN. CNN, as such, is not directly used. However, stacks of CNNs have been used for single image super resolution, and the results for such a model was significantly better than the deterministic algorithms. So common deep learning methods usually take one of two paths. Since learning methods require the calculation of a loss, so it is essential that the output is of the same dimensionality as the ground truth. The low resolution image is a matrix of order n cross n, but the high resolution image is a matrix of order, let's say, 2n cross 2n. So the dimensionality of the of the input and the output don't match, and as such we must upsample the input to match the dimensionality of the output. This upsampling has to be done before the calculation of the loss in order for our model to learn anything. So usually deep learning methods follow two methods. Either they will upsample in the beginning and then try to learn the difference between this upsampled image and the ground truth image, of course by means of loss, or a, a late upsampling, which is that after learning the features and generating a subsequent feature map, then we produce an upsampled image. So basically feature learning is done, features are learned over the low resolution image, which allows lesser computations. Some other advanced methods such as attention, recursion, etc. have also been used, and sometimes instead of directly generating the high resolution image, the residual, which is the difference between the upsampled low resolution image and the ground truth images, are calculated. By ground truth here, I don't mean the actual ground truth. I mean that the the generated output of the model. Basically, the model uh, generates the residual, and that is added to the upsampled uh, image, which was produced at the beginning, and then these two are added to produce the final high resolution image. So some common architectures for deep learning methods. So the first way that I mentioned earlier, which uses early upsampling. So there are many common methods for early upsampling. So some of the methods are SRCNN, IRCNN, and DNCNN. So these three methods, they basically consider a linearly stacked network where all the components are stacked linearly. And of course, these methods uh, implement early upsampling. There are some minor differences between the implementations of these methods. For example, SRCNN is a very basic model, since it was the pioneering work in single image super resolution. It basically stacks multiple CNN layers to learn the mapping between the upsampled high resolution image and the ground truth. VDSR is a network which learns the residual, or the difference, which can be seen from the figure on the right, on the top right, where there is an additional skip connection between the input, and which goes into an addition operation, basically, which means that the upsampled input is added to the residual to get the final output. In late upsampling, there are many architectures, but one of which is ESPCN, and here basically the mapping is learned on the feature domain, and then those features are projected onto a higher dimensional matrix to get the final high resolution image. So how can this be extended to video super resolution? So video super resolution can be seen as an extension of single image super resolution, since low resolution videos can basically be considered as temporally related sequence of low resolution images. However, there are some additional challenges and some advantages in video super resolution. So the challenge is that because it's a video and different frames of the video are temporally connected, it means that the position of different objects will change from frame to frame. However, the positions will not skip or will not jump from one coordinate to another. Because we go frame by frame, so there must be some kind of flow in the movement of the objects. So the objects in different frames have to be aligned properly for us to leverage any kind of information from multiple frames. And that which leads me to the advantage that in single image super resolution, we hardly have any additional data. But in video super resolution, we have an additional temporal information to help us, which is that, let's say I want to uh, uh, produce a high resolution version of a frame, a current frame, let's say. I have the past, let's say the past n frames and the future n frames to help me to do this, uh, to provide me with uh, more information for this process. However, as I mentioned before, in a video, the objects will have a particular flow in changing positions. So these object locations have to be aligned properly with respect to the current frame, so that we can use the information from all the support frames. Support frames are the frames which are not the current frames, or the information from these frames. We are leveraging the information from these frames. So these have to be aligned properly, otherwise we cannot use this information. So of course, in video super resolution, for temporal alignment, several deterministic algorithms have been used, but their performance are not as good as data-driven models. Initially, most deep learning models wanted to estimate something called flow, which is, as I mentioned, is basically the change in position of different objects from one frame to another. And we need to align the different objects in the other frames. As I mentioned, they're called the support frames with respect to the current frame. Otherwise, we cannot leverage on the information from the other frames. So the models which estimate the flow, the output is basically, the output of such models are the images where the objects, the moving objects, are warped to the properly aligned positions, meaning that the objects are warped to the position which is in the current frame. So the state of the art for flow estimation is FlowNet 2.0. So in this model, they used 3 tricks to train this model, and which basically made it one of the best in the field. Significant subsequent improvements on this model have been done, but these can be considered as minor computational improvements and not major changes in the idea of the network. So the 3 tricks they used in this model are: first, they made the dataset progressively more difficult to be aligned, which means that in the beginning they started with easier data, meaning the flow is only 2-dimensional. There's no change in 3-dimensional lighting and as such and such stuff. But progressively they made the dataset more difficult, or the flow in the dataset was more difficult to be estimated, because 3D lighting changes were introduced. The second trick that they used was iterative computation, which they did by stacking multiple networks on top of each other. Here it can be seen by the different FlowNets, FlowNet C, FlowNet S, FlowNet S, which have been stacked together. And finally, a separate network was learned for small displacements. For this separate network, they had to generate a separate data set. Because deep learning methods were outperforming deterministic algorithms in almost all fields. However, in the case of small displacements, the deep learning methods were not working as well. The reason behind this is because there was not enough data for them to learn from, or not enough data with small displacements for them to learn from. But deterministic algorithms performed very well on images with very small displacements. So to solve this problem, they had to create a separate data set with images having small displacements in objects. And so they also introduced a fusion module, which basically fuses the 2 kinds of networks. The first is a stack network for large displacements of objects, and the second one is the network for small displacement of objects to estimate the flow. So later this idea was improved by considering the fact that the warped images, or images which are generated from flow estimation models such as FlowNet 2.0, producing such warped images is extremely difficult, meaning the warped images are prone to errors, and this highly influences the super resolution results. And hence, a new model was proposed which does temporal alignment on the feature level. This model was called TDAN, which also used deformable CNN to enlarge the receptive field. So this also introduced the problem that the aligned features from multiple frames had to be fused together to form one set of features. Note that these are features which have to be fused. So the currently the best model for video super resolution is called EDVR, and for temporal alignment it uses something called PCD, Pyramid Cascading Deformable Alignment. So the good thing about this model is that it uses ideas from both flow estimation networks and from TDAN. So in flow estimation networks, or I think in general in basic computer vision, pyramid networks or learning features from coarse to finer levels is considered as much better for in terms of learning. Cascading, as we saw before, that cascading or stacking multiple networks helps in learning features better, and deformable is because of their use of deformable convolutional neural networks. For fusion of the different features, they use something called TSA fusion module, which basically calculates the attention or calculates the contribution of neighboring frames to the current frame, and also it computes the contribution of different patches in the current frame to generate the high resolution frame for the current frame. So for future work, there are still some challenges to solve in video super resolution. These problems are because current models, they are trained for a particular upscale factor. We still don't have models which work with arbitrary scale factor, or basically we don't have models where the scale factor is also an input. So we would love to have models which can take the scale factor as an input and produce a network which can generate high resolution images of that scale factor. The second challenge is that the degradation, or because we consider that from high resolution image to a low resolution image, there must be some kind of degradation. Otherwise, why was there a loss of information? So this degradation, or the process of this degradation, is not known to us. It may not even be one operation of degradation. There may be multiple operations of degradation. So we don't know how this degradation was done, and so we still need to figure out models which take this into account. Because most models, most current models, they use to simulate degradation, they use a particular algorithm, let's say bicubic interpolation. So the danger is that the model will now learn the pattern of bicubic interpolation and not of natural degradation operations. The third problem, which we are currently working on, which me and my other lab mates are working on, is how to combine temporal information with spatial information. So because it's video super resolution, we have temporal information because it's a video, but we also have spatial information, which is also leveraged on in single image super resolution. So we must find a way to combine these two in order to get a good high resolution result. Of course, the old problem that we don't have good enough metrics for image quality assessment must be solved, or we must have good metrics which correlate with human perception of how good an image is. And the final problem is that because most problems right now, they contain a high resolution image as ground truth, but we want to have models which can learn or which can generate high resolution images in an unsupervised manner. So this is also one of the challenges that we need to solve. To finally conclude, the field of video super resolution is full of exciting challenges. Data-driven methods have outpaced the deterministic methods, of course. However, like all data-driven methods, methods for video super resolution have to be learned better. But in order to be learned better, we need better learning algorithms, better architectures, we need higher quality data, we need more data, and we need some particular theoretical breakthroughs in order to have such developments. So this concludes my presentation. Thank you for listening.